So we'll start with Thomas Lorünser. He's a senior scientist, project manager, and a team leader at the AIT Austrian Institute of Technology Center for Digital Safety and Security. He holds an MSc and a PhD degrees from the Vienna University of Technology, specializing in telecommunications, cybersecurity, and cryptography. Over the past 2 decades, he has led and contributed to numerous national and international research projects in the fields of secure and privacy-preserving data processing, cloud security, applied cryptography, and quantum cryptography. Welcome, Thomas. Thank you.
Thank you very much for the introduction and for having me. So this session, as I interpreted it, should be more disruptive. So I try to follow this idea, and let's see what I can do. So just up front, I wanted to say that I really like MPC. It's a fantastic technology, and I think I was fascinated when I first saw all these secure computation technologies which are currently under development. They have a huge potential and serve as pets, can protect privacy data, but can also protect business data, as we have seen. So I'm working at Austrian Institute of Technology, and I jumped on the bandwagon a bit late, but the last few years we had some MPC projects in our department, and we really tried to promote the technology to industry. So I would like to report my experience from some projects I had, and the problems we suffered, and the challenges and the lessons learned from that. So I'm jumping right into the topic. So I will try to explain a bit the project and the context quickly and see what problems we had. So the first one, I mean, the sugar beet auction was already mentioned, the famous practical presentation. I mean, it was super practical at that time, but I think the people were sitting together with 3 notebooks or something like that in a room and had to enter the numbers. So I'm not sure if this is still valid for practical applications nowadays. So what we tried to do in a first project with manufacturing industry partners is to come up with a modern version of a marketplace for manufacturing industry, for manufacturing capacities of machinery, so that you can easily outsource maybe semi-automatic or even automatic and have best price offers and try to build a platform based on MPC. Because contrary to the private sector where people can live with centralized systems, like we know all of them, in the manufacturing industry we found out that the prices are sensitive, capacity management is sensitive information for them, so they don't want to easily share that. But in order to compute and having a market, you need this information. So the idea was to build it on MPC. And we heard multiple times, you can have many input parties, so the natural way, and not everybody wants to be an MPC node in such a system, so the natural way is to go to the outsourcing model and to build a system like this. So the MPC part was rather straightforward. I would say we have nice frameworks, nice technologies. But then if you try to communicate the security, for example, things like the non-collusion assumption is easy to understand if I am an MPC node, but it's not easy to understand because you communicate with a platform. Even if the platform is doing MPC, how can you ensure that there are independent nodes not colluding and computing a secure result where they don't leak sensitive information, for example. This was a huge communication and security problem for us. And complexity must be hidden. We have seen that today, so I can only support what the people from the previous panel said. So, but only looking at the computation of MPC is easy. This is something you can control. But later on, if you build a whole system, and you want to keep it decentralized, it gets really complex. And especially if you don't have a very static scenarios where our input parties are known in advance, they know each other. So if you don't have a setting like this, it can get really complex, was my experience. And then sometimes we even found out that in the case of this auction, there was even the problem of correctness. So sensitivity or confidentiality of the data was important for the people, but even more important was that the correctness of the result, so that they have not been cheated. the platform. So what we tried to do here is that we combined it, for example, with zero knowledge proof systems, so that you also get a proof that the result was computed correctly. Because what they couldn't stand with is basically being cheating and not considered their bid. So this putting all the things together get really complex and was not so easy to sell. So we built the prototype, and as multiple projects I had in the past, after the prototype, it did not really continue. So we want to generate innovation. That was a really good question also today. How can we really generate an innovation? And innovation is only valid innovation if it hits the market. So this is something we should really discuss also as a community maybe. Another project we are having is called Slot Machine. This is basically where we try to optimize landing slots in air traffic management at airports. So airports have a very dynamic scenarios. You could imagine many airlines having the delayed flights, changing conditions, but you have only a given infrastructure and you want to optimize the use of the infrastructure. So if you look at airlines or something, then operations knowledge is their basic asset. So if you want to globally optimize over the infrastructure you have, they have to somehow pull the data, but this is operational data which they don't want to join. So we build a system based on MPC, for example, where you can optimize based on airline preferences. And we used a similar approach which we have seen before. So I think what emerges if you look at these systems is patterns. We often heard these patterns, you're outsourcing computation, you have remote nodes somewhere. So maybe a way to formalize that is also like we do in software engineering, is to have privacy patterns, software patterns, and be more generic there. And what we also found here, because optimizations get quite tricky in terms of computational load, so you also have to learn to deal with trade-offs in practical, because you want to have real-time, whatever real-time means in your use case. You have to deal with real-time issues sometimes, and then you have to do trade-offs. You cannot do a full optimization like you would do in the plain text world, but you maybe could live with heuristics. You maybe can do close to optimal solutions, but still use MPC. So optimization for us was not only to optimize the algorithm to make it MPC friendly as good as possible, but also think about meta-heuristical approaches which can be applied to do heuristics and to trade off security. If you want to have things deployed, sometimes we also combine it with genetic algorithms to have a trade-off there. So this was, and interestingly, I mean, I spent also some time in trying to implement pets and sell pets, and they ended up in the graveyard. What we're seeing now, and I think in the privacy domain, we have lost a lot of potential there. But what we're now seeing and what I have shown to you is basically the idea of using it to protect business assets. So I think and even in the blockchain world, we see it when it comes to money. There is a huge push in not protecting personal data, but sensitive information for businesses. So this is a huge push in general, but still we should also use it to protect privacy data. So what we are currently doing is a project where we roll back, and now many people try to think about biometrics, and biometrics is an authentication as a method for authentication where you cannot easily change your identity like into passwords. So this is more sensitive information, biometric information, and therefore if you deal with biometrics, you have to be more careful. So there is also a chance to work with MPC tools and privacy enhancing tools there, so that you have more control about your biometrics. And here, for example, we are working on an automated border control system at the airport. And here you have the problem that you want to screen the people and check against, for example, a no-fly list. A no-fly list is intrinsically a centralized system where different people share terrorist information or something like that. And if you want to check against that list, you have to necessarily send the fingerprints or the faces to the central database. And this is something we don't want to do. And here MPC systems could help, or cryptography could help, in terms that you only learn the biometrics of suspect peoples, but you don't interfere with the privacy of innocent people. So you can do that if you have a secret shared database and you do matching in a privacy preserving form. So this was our idea about this. And now when it comes to implementation, so it's a mess. There is another messy picture. I like messy picture, but this just describes the complexity. But I think we have a huge chance today because in Europe, we also have these data space initiatives. We have many initiatives. We have Data Act, we have AI Act, and these somehow belong together and come together. And for example, with this data space initiative, we should have a chance to somehow promote pets and to build into the system. So our idea is convenience goes overall, is my experience. If it's not convenient, people won't use it beyond particular experts doing niche solutions. So we need a way, and this is a chance, I would say, if we manage to build this in a standardized way, as we heard today, and make it somehow data space compliant, maybe there is a chance for people to more easily use it. So, and just to sum up, so this was our experience there. So not easy to sell the solutions. And we heard it also in the first letter, which was read. We really need to incentivize people, because what I hear all of the time is if the goal is to be compliant, I just have to follow the state of the art. And if MPC is not the state of the art, I'm not going to use it. So either we have a regulation to make it somehow state of the art to use this, or other means to do that, or we have to incentivize to enable other things or whatever. So this is really hard. And just to sum up a bit with the quantum approach, we're also experimenting a bit with post-quantum version, but a rather extreme one. So we're trying to combine it with quantum oblivious transfer, which is a technique very similar to quantum key distribution. And I would say our results are pretty, at the moment, it's very early research results, also on the quantum oblivious transfer, but this is not solving many problems. It will also be rather niche, it's rather slow. So there you can, I don't know, every hour you can do an MPC computation, depending on what you do. So here a lot of more research is necessary to make this faster, but it still has the limitations. So I would say we should also focus on the post-quantum versions, which rely on classical post-quantum, oxymoron, on post-quantum technology. So to sum up, so my experience is there is no ideal solution. So we live also a bit in this triangle. I would say convenience versus security, many nodes, scalability problems. The more nodes I have, the more distributed trust is. But in the end, you're using 3 nodes. So why? If I have 100 nodes, I would compute distributed trust, but this is then a performance issue. We have convenience issues. I mean, it's a distributed system. We heard this today. Setting up your things are a nightmare. When I had this in projects, even IT people don't want to set up that. That they say, okay, why don't you trust us? We set up a server for you and it's fine. So this is the real world problems, I would say, if you want to promote the technology and implement it. So therefore, we need benefits which immediately materialize, I would say. Not something I can reduce my risk or the risk for the data I have, but we need something which immediately materializes. Whatever, to being better compliant, support by regulation, to have other use cases which are only allowed, as we heard today, if I use the technology, which I cannot do without, or something like this. Otherwise, people won't really adopt the technology. So this was, unfortunately, I would love to have to sell all of them, fancy MPC systems, but so far it didn't work out. Thank you.
Thank you, Thomas. And thank you for this wrap up, which is, I guess it's the whole point of what we are aiming at this panel. Thank you for that. Now we'll move to the second speaker. That's Idoia Gamiz. She's a cybersecurity researcher at Tecnalia, where she is part of the core cybersecurity and DLT's research team in the digital unit. She has a degree in mathematics from the University of Basque Country with a specialization in applied mathematics and a master's degree in mathematical modeling, research, statistics, and computing from the same university. She has been working with secure multi-party computation since she started her master's studies, and she has authored, among others, the article Challenges and Future Research Directions in Secure Multi-Party Computation for Resource-Constrained Devices and Large-Scale Computations. Thank you, Idoia.
Thank you very much for the introduction. As he said, I work at Tecnalia, which is a center of applied research and technological development in Spain. And today I want to speak about some general limitations of that we have found when trying to use this technology in our project. And I want to focus on what we have learned when trying to address this challenge. So when at Tecnalia, we usually divide or categorize this challenge into two main categories: performance and complexity. And depending on the requirements of the specific project, we sometimes have some problems or others. So to be honest, when we have a project where we have to apply secure multi-party computation, we usually aim to achieve a first proof of concept, but the problems comes when we try to scale the solution. So the real question for us is what happens if we try to scale SMPC? So scaling the solution is not just a mean of making something bigger. When we work with this technology, sometimes scaling the solution means working with extensive data. But other times, scaling the solution means scaling the solution to real-world use cases where we have to work with resource-constrained devices, or other times we need to work with a big number of parties. So depending on which scalability path we follow, we have some problems or others. In the case of extensive data, we usually have very slow operations, and we have a high demand of resources. So we can also have bandwidth bottlenecks or even memory issues to store and share a vast amount of data. In the case of resource-constrained devices, these problems are even more pronounced because we can have devices with short battery life or low resources where, for example, the bandwidth problem, it is not just a mean of speed. It can be a mean of, if we have a device that can't handle the communication, the whole system can stop. And in the case of working with large number of participants, we see more problems related with complexity, in the sense that in secure multi-party computation, or at least in the traditional way of computing it, we need a predefined network where all the parties must communicate with each other with peer-to-peer communications. Furthermore, if we need synchronous communication between the parties and we have a lot of devices, sometimes this in real-world scenario is not easy to achieve. So that is, like, in general terms, what we have seen, but what have exactly done in past projects and what are we trying to do in ongoing proposals? To let you understand how we work in Tecnalia, we usually have two types of projects. First, we have private projects where we directly with customers, and then we also have public projects where we work together with other partners to create a privacy preserving solution. But in both cases, sometimes we need to, or most of the times, we need to apply our privacy preserving solution to an already existing system. So if this system is not prepared for this type of computation, we can have a lot of troubles. So what have we done? We have already success in statistical operations. With this, I mean simple operations between a fixed number of parties. And in these cases, we achieve without technical overload, and we meet the deadlines of the project. But what happens if we try to apply this to more complex scenarios, like artificial intelligence scenarios? We have seen a growth demand of this type of projects. In the past, we were asked a lot to implement secure multi-party computation for simple operations, but nowadays, most of the projects, both public and private, want us to integrate the privacy preserving solution to train machine learning or deep learning models, and this can be very slow. So we usually look for other solutions, like using federated learning for the training, and integrating secure multi-party computation only in the aggregation phase. Even in this case, if we have a lot of parties, sometimes we can also have problems because of the predefining network and the peer-to-peer communications that must be repeated in each round of the federated learning process. So sometimes we have to look other alternatives like homomorphic encryption or differential privacy. So for going from this challenge to solution, 2 years ago, we decided to conduct a systematic literature review. The objective was to answer 2 research questions. The first one was how to adapt this technology to restore constrained devices. And the second one was how to adapt this technology to large-scale computations. The whole process is available online, so you can look in the internet if you are interested in the process. And we analyzed a lot of studies, but because of the inclusion and the exclusion criteria, we end up analyzing 19 studies in depth. We categorize these studies into a lot of categories, but I want to focus in the technique that they use. So regarding the technique, in big data scenarios, we see that they use a lot of mixed protocols to switch between plain text and ciphertext or to use different types of secure multi-party computation protocols. And I think that this is a good path because, in my opinion, we sometimes try to apply secure multi-party computation for everything. And if it is a technology that has its performance limitation, it is very important to know when and why we have to use this technology and to divide these operations as much as possible. So another option is to use protocol optimizations. A lot of the articles that we have found take a protocol and optimize the protocol. And then in the case of restore constrained devices, we have seen a lot of outsourcing the computation or to the cloud or to hardware-based trusted execution environments. So what's next? At Tecnalia, we want to follow 2 paths. First, we want to bridge the gap between the solutions found in the systematic literature review and the practice. We want to adapt and implement these solutions in real-world scenarios. And also, we want to search for other type of technologies that were not found in the systematic literature review, but that can be very, very useful. And this is the case of delegated secure multi-party computation. In this case, instead of, it is very related with secure outsourcing, but instead of outsourcing the computation to the cloud or to a trusted execution environment, they delegate the computation to another type of party that are the agents. So in this case, the clients are the ones that are the data owners, and what they do is they delegate the computation to the agents. This has a lot of advantages in terms of complexity. The clients do not need to communicate between each other, so there is no need of so many peer-to-peer communications. The clients only need to communicate with the agents because they secret share the data with the agents. So it is good for a large number of clients or data owners. And then in terms of performance, it can be good because the clients do not need so many resources, only the agents do. And in this sense, we can work with more type of devices. But we have to be careful and we have to consider other disadvantages or challenges that are not solved yet. That is, how can we, in terms of complexity, even if the clients do not communicate with each other, they need to communicate with all the agents. So we also need a predefined network in some way. And also, we need certificates to authenticate both the agents and the clients. And in terms of security, there is a new challenge, like how can we know that actually the agents are going to compute what we want to, like as clients want to compute. So in conclusion, we think that this technology is a powerful tool, but real-world adaptation needs careful adoption. So the goal for us to make this technology practical and scalable, and to do so, we want to combine existing research with other alternatives like delegated secure multi-party computation. That's all.
Thank you very much, Idoia. And again, thank you for the wrap up at the end, because this will help us, I guess, to direct better the Q&A that will follow. And following, we'll have Christian Rechberger. He's a full professor at TU Graz, directing the area of cryptography and privacy at ISAC, and co-leading the area data security at No Center. Previously, he held various teaching, research, and visiting positions at DTU Compute, ANS Ulm, KU Leuven, and MSR Redmond. Thank you very much, Christian.
Thanks a lot, Vitor, for the nice introduction. Thanks a lot for the invitation here. It's a very good event. One thing I would like to add to the introduction is that I have actually two hats. So what you heard in the introduction was with my university hat on, basically. My second hat is being co-founder and chief scientist at a spin-off from my group called Tecnalia, which is now developing into a startup. So the core product idea of Tecnalia is basically to address some of the pain points that we have heard here in the discussion already. I mean, in some sense, it's of course a hindrance to deploying of MPC, but in some sense, I'm also happy to hear this because it sounds like there's future demand, namely to address all these orchestration issues when it comes to setting up this network of nodes. Even sysadmins feel it is a pain, all this kind of stuff. So the idea of this company, and this is not the point of my talk here, just as a way of intro, is to make this easier, basically offering this as a service to other users or even other deep tech companies. So what I would like to do with this talk is basically to use this rhetoric vehicle of myths, of myth busting, to get a few points across. I mean, will be quite basic points, and it's a bit crude, but I hope anyway to instigate some discussions with this. The first one is that, and we have heard a variant of this earlier today already, is MPC is mostly bound by communication and bandwidth. Hence, you can really throw hardware at it to make it faster. Hence, it doesn't scale. Meaning for big use cases, it's not the right fit. Yeah, and I would like to address and potentially bust this myth. And the way I do this is just by means of one simple example. The use case would be privacy-enhanced biometric uniqueness checks. There's various ways to do this. I list here two deployments. One is by the Red Cross, the other one is by World ID. So the basic idea is to not have a central database which contains some biometric information, but delete this database and replace it with a distributed version of it that does some uniqueness checks. Basically, it can be very simple. Scan for this database, checking for similarities or matches. The trouble is when you want to be fast doing this, and this database becomes very large, many millions of entries there, people. So what we did was to, first of all, throw a lot of crypto engineering resources. I did look at the best protocols in the literature and then improve upon that. And the number that I have here on the CPU side, meaning a regular off-the-shelf computer, the number is below 1 million of those code comparisons per second, which is already quite a bit larger than what was possible before. My point here is that in this particular case, it was possible, hence disproving this myth, basically, to throw expensive hardware at it, because we were at a trade-off point where we could assume low latency connections between the MPC nodes, and hence using really powerful, of course also expensive hardware in the form of H100 GPUs. If you're not familiar with those, these are like flagship products of NVIDIA that frontier AI companies also use to train their models on. Cost tens of thousands of euros, and we use quite a few of them, not only one. But anyway, being able to throw hardware at it, we could increase the performance here by 3 to 4 orders of magnitude. That's something that tipped the scale in the sense that only with this it wasn't possible to deploy the system in production at this very large scale. So this is already my first point, this myth in some sense busted. MPC can scale. You can throw hardware at it. Of course, this is now was a setting with low latency nodes. The road ahead, I see, is quite exciting because there's more and more research on constant round protocols, for example, arithmetic garbling, homomorphic secret sharing, which allow much more of these types of trade-offs. We reduce the amount of communication, the amount of rounds at the expense of more computation, yes, but then we can throw hardware at it to make it scale. So that's something that, yeah, companies that want to scale can do. And so far, MPC was kind of thought to be not able to leverage this. And my point is, we can already do this now, and we will be able to do this even more in the future. Yeah, my second point, here I have to take a small step back. We talk about secure multi-party computation here a lot. There's another umbrella term, zero knowledge proofs, for related privacy technology, privacy enhancing technologies. And it has some overlapping use cases, but in some sense also quite complementary properties. And often it would actually be nice to combine the best of both, have integrity and various properties given to you by zero knowledge proofs, and have the privacy guarantees by MPC networks and MPC computations. And the starting point is quite a negative one. We get already quite an overhead with MPC. We do get quite an overhead, even more perhaps, with zero knowledge proofs compared to plain computations, I mean. And what you would expect is that these overheads multiply and hence costs explode. And this is basically a bit of a wishful thinking. Yeah. The last years, this should not be considered to be the case anymore. There was a nice paper in 21 by colleagues in California that showed for an important example that the costs are quite a bit lower. Since then, there's quite a number of works. I will not go through the list here. This is just to show you there's an acceleration in this particular type of research. What I would like to show you in my next slide is a concrete implementation of this kind of stuff. So please bear with me when I walk you through this slide here a bit. Let's see. So on this axis here, we have the kind of the size of the problem. On the left side, smaller size problem. On the right side, a larger size problem on a logarithmic scale. On the other axis, you have basically the time that is spent on just proving or doing the combination of proving and MPC. So as you can see, of course, the larger the problem, the more time you have to spend. But the point is now, these bluish lines, the dark blue and the yellow blue, the lighter blue ones are the combinations of MPC and ZK. They're just two lines that show the progress in the development 1 year ago and like half a year ago. And what this means is that by now, for this type of proof systems, we basically have no additional overhead compared to ZK. Yeah. The good news is that, so this is an output of the company. There's no patents, there's very liberal license. This is accessible to developers and other companies in the form of libraries called CoNoA and CoCircum. If you don't want to set up your own network doing this, there's then a commercial version that runs this in the network for you. The point is, yeah, this is already now usable. Concluding my second point here, to some extent, this combination is possible because it can be cheap. There's a bit of a caveat here. Should be honest, this basically works well for discrete log-based proof systems, which means pre-quantum proof systems. The road ahead here for us is to do something similar with proof systems that are not based on the discrete log assumption like hash-based proof system and so on. It's not directly obvious how to make this as efficient, but there's several ideas in this direction. So there's a clear road towards the best of both from MPC and ZK. Yeah, this brings me already to my last point, post-quantum security. So the 3 points that I am listing here were kind of inspired by the by the setup of the panel proposed. And this was one of the discussion points. And again here, for good reasons, we hear a lot, now simplifying of course, but post-quantum is much more expensive than pre-quantum. We also see this in this maturation of the algorithms and the technology that is now going through international standardization, for example at NIST, but also at many other places. At ISO, when it comes to public key encryption, public key signatures, key exchange, we see now the standards that are coming out in the last years from these processes. They give us this property of contractor to be secure even in the face of future large enough cryptographically relevant quantum computer. I mean, they may or may not exist in our lifetime, but the point is people will expect this kind of property anyway soon. And the property of these algorithms is that usually they are quite a bit more expensive in terms of signature size, ciphertext size, computational costs, and so on and so forth. And of course, it's natural to assume that this applies to MPC as well. I mean, the MPC situation is a bit more nuanced because luckily we have information theoretically secure MPC protocols, so then this discussion doesn't start at all. In other cases, it's possible to, for example, in OT-based systems, it's possible to simply swap out the building blocks that are pre-quantum with such that are post-quantum, but then we have this additional cost. So the way I bust this last myth here is by mentioning a recent paper of ours where we look at a particular very versatile tool that you built with MPC and also use for all kinds of MPC use cases, namely oblivious PRFs. Also the private set intersection and private contact discovery use case that Thomas mentioned in the first panel uses this kind of underlying building blocks. And what we discovered now is that with a lattice-based PRF that is contracted to be also post-quantum secure, we're actually faster both on the client and on the server side than any so-called pre-quantum secure PRF. So this gives hope that there's more nuggets to be found that further disprove this last myth. Yeah, you can find the paper here, the link. The road ahead is basically that there may be more of those surprising algorithms to be found, and hence we shouldn't be worried about additional costs of post-quantum security. Yeah, with that, I'm already at the end of my talk. Thanks a lot for your attention. I'm looking forward to the discussion.
Thank you very much, Christian. And from Christian, we move to Christian Brendel. Christian Brendel has a degree in physics and mechanical engineering from the Friedrich Alexander University in Erlangen. He holds a PhD in theoretical physics from the Max Planck Institute for the Science of Light. He was among the foundation team of Tools for Humanity, where he played a key role for launching the World Project. As head of AI and biometrics at Tools for Humanity, he works to develop privacy-preserving biometric recognition systems, which he will present. Dr. Brendel has also worked in the development and deployment of the anonymized multi-party computation of the World Project. The floor is yours.
Right. Thank you. Thank you for the invitation. Thanks for the introduction. Little disclaimer, as you've heard, I'm running the biometrics team at this company, so I'm actually not necessarily the person on the team that is actually developing those things. I'm more of running the team that is actually dealing with all the side effects of such a system that is deployed now, which can be particularly painful at some point, but we'll come to that. Now today, I want to explain a little bit more about the system that we have in place, which we call AMPC, which is just like our flavor of a secure multi-party computation protocol that we are running for a biometric recognition system. Now, to start with, why do we actually build such a protocol? First answer for that is because we have a business problem to solve. And our business problem to solve is basically to build an kind of infrastructure, like an identity infrastructure on the internet, which is anonymous on the one hand, and which only allows every person on Earth to just enroll once to the system, and really only once. We decided to do this with some biometric recognition technology, just simply because it's the only and the best technology that can work on a global scale, and that can also be like accurate enough so that it's a reliable system in the end. Now, when dealing with biometric data, of course, you have a bunch of legal requirements, among them GDPR and the CCPA and so on and so forth, which makes things, of course, a little bit challenging, but also for a good reason. Now, with that in mind, and also with the mission of the company of like being as privacy preserving as possible, we said, okay, let's go to the very extreme of the spectrum, and let's build a system that can really only reveal the single bit of information that we actually need in order to issue such a world ID, which is in our case basically just the information of whether a certain person has already been part of a set, or if the person hasn't been part of a set. So it's really just a single bit of information that we want to reveal and that we want to like the system to basically return. Now, let me talk a little bit about the biometrics to lay out the foundation. So we decided to use iris recognition for that, simply because it's like the most accurate biometrics out there. What you use for that is obviously the iris texture, so you could really see it nicely here at the image here. It's an iris captured under infrared illumination, and this infrared illumination basically highlights the nice pattern of the iris texture, which has like a crazy amount of entropy in it, so that you can use it for a recognition. How it works actually is basically that way. So you start with the pixel image, which is just a 2D array of like pixel values, and then you run this feature extraction, which is basically just a small word for actually quite a big engine that's running there. So it uses countless computer vision algorithms from semantic segmentation to detect which pixel is actually iris or which pixel is a reflection, to like some spoof or anti-spoof classifiers, like detecting whether there is a cosmetic contact lens or whether it's a real iris. And in the end, what it basically returns is just a simple 2D so-called iris code, which is just like, as you can see here, in this case, a 3x3 matrix of zeros and ones. In practice, it's actually a lot bigger, like I think 16 by 256 at the moment, that we can use for recognition. Now, these iris codes have the peculiarity that you can calculate a similarity with them, or basically a Hamming distance. So what you do in practice is you take two of those iris codes, you calculate the Hamming distance, which is basically just like counting the number of bits that are different. And then if this is below a certain threshold, you say this is the same person, otherwise it's a different person. And it works with incredible accuracy in practice. Now, what's our system? Our system looks like that. So on the one hand side, you have on the very left the orb, which is basically just like a fancy camera. So it captures the picture of the iris of a user. It runs this whole pipeline on device. It, in the end, returns one of the two of those iris codes for both eyes. It signs those, sends this data to the phone of the user, and then deletes the data from the device. So it's basically self-custodial. The user, in the end, will just have like a iris code issued, which is tamper-proof because of the signing. What happens then is that the user will basically split this iris code into 3 pieces, and we'll get deeper in a second. And we'll send these 3 pieces to like 3 individual nodes here running by Berkeley, the FAU in Erlangen, and Nethermind. And they perform our AMPC protocol, which is our flavor of SMPC protocol, to basically calculate whether the incoming iris code shares match with any of the other, at the moment, I think 18 million iris code shares that are in those databases in like below 30 seconds. And then basically just returns whether this person has already been here or not. If not, we issue the credentials or we issue the world ID. Now, that's the overview. Now going forward, I take a step back for those we have lost in the audience and all the technicalities before. Maybe it's not a good point to pay attention again, because I just want to like roughly explain how things work. For some people here, it might be a bit boring maybe. So to start with, what is the secret sharing that we're doing? And for that, I would like to leave a little bit the domain of the biometrics and just start with a very simple example, which is this one here, that we have 4 colleagues, Alexander, Beatrice, Charlotte, and Daniel. They are sitting together in the cafeteria and they are thinking, okay, do I actually earn more than the average of the team or do I earn less than them? Of course, no one of them wants to reveal the salary. So what should they do? They cannot simply just say, okay, I'm earning this, 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 and that, and then build the average. But what they could do is like a so-called additive secret sharing. So every one of them just has 2 pieces of paper and writes 2 numbers on them. And these numbers just add up to the real salary that they have. In this case, from whatever Daniel, it's -8, 13, which add up to 5. And Daniel gives the 2 pieces of paper to one to node 1, the other one to node 2. The individual nodes, they do not know anything about the individual salaries of the user. It's basically just data garbage. But what those nodes can do is they can calculate the average for their specific subsets. So they do this, get 3.5 and 6.5 in this example. You can add those up and you also get 10, which is exactly the average. Very simple. And as simple, at least on a conceptual basis, is actually what we do with those iris codes, which is basically this one here, which was our first version of this whole protocol. So what the orb does, it calculates these iris codes, which are basically just 2D arrays of zeros and ones. And these iris codes are basically additive secret shared and being sent to databases. You can see it here, and like whatever the first one is separated in like a -5 and a 6, a 0 and a -3 and 3, and so on and so forth. And now what this whole SMPC setup was doing was not just calculating the average, basically just calculating the distance, which is not too different. And in the end, we could issue these world IDs. Now, this whole setup had a tiny problem, which was that we needed to send the raw data in here. So this encrypted uniqueness verification service got the raw data and then was split there. So in order to also mitigate that and to mitigate the problem that we did not want to reveal any distances, we really wanted to reveal only like the 1 bit, yes or no, this person is here or not. We needed to basically go to at least 3 nodes. Now, among other things, we switched our secret sharing scheme then to like a Shamir secret sharing, which was necessary from a technical perspective for what I just explained, but also gives us the possibility to maybe later go to schemes where we can say, okay, we want to have like 25 nodes and only 10 of them need to participate for this protocol. So we switched to another sharing scheme, which I think I don't need to explain in this round here. And then among this and other things, for instance, like a resharing of the encrypted distances. So what basically happens is that the client shares the iris codes with the Shamir secret sharing. The whole protocol calculates distances, so like a intermediate result of that. These should obviously not be revealed to other parties because then we might reveal the distance. So there must be a secret, additional secret sharing within the protocol, which happens here to calculate the distances. And in the end, we just reveal the 1 bit of information, whether the user has been there or not. There's a bunch of other technical challenges, for instance, that we needed to basically exploit the iris code from like a bit vector to like a integer value, 16 bits. We have overall like 12,800 bits, which that's the compute explode. We need to take into account like effects that happen in practice that, for instance, for irises, you have a ring-like structure, but you morph it into like a 2D pattern. So at some point you need to decide where do you want to start the feature extraction, is it here or there? So in the end, you basically need to compensate for this effect and do this whole calculation like 30 times for 30 different rotations. You need to do it for both eyes, and you also need to take so-called masks into account, which makes things a lot more complicated, which is basically the trick in order to mask out iris code bits, because there might be a reflection or there might be an eyelash or like an eyelid covering the real iris texture, which is of course not useful information for any biometric system. So yeah, all in all, there's a lot of like details in there, and there was a lot of work being done to bring this on scale. But now, like we're operating on a database of like 18 million users in this database on 3 different nodes, and like one of those uniqueness checks is happening below like 30 seconds. Also, with like great help from Teseo and Kristen here, we achieved that. Now, as a summary, like maybe 2 things to remember. We started with like an SMPC setup. It splits the code into puzzle pieces, and we used those puzzle pieces to calculate the similarities. And then we developed the whole system further to which we call make it an AMPC, which makes it anonymous, which is basically a system that only reveals whether you are a match or a non-match and no other information. This is really just like the single bit of information that you would need in order to run such a system. And with that, I want to thank you for the attention.
Thank you, Christian, for sharing your perspective on this. And we move to the last speaker of the day, which is Liina Kamm. She's a senior researcher and a principal investigator at Cybernetica. She researches privacy-enhancing technologies and their uptake and the privacy and security of AI systems. She has a PhD degree in computer science from the University of Tartu. She's Cybernetica's principal investigator for the Horizon Europe project, CHESS, which means Cybersecurity Excellence Hub in Estonia and South Moravia, and the Office of Naval Research, ONR, project PyMachine on machine optimizing machine learning algorithms for secure multi-party computation. Thank you, Liina, for being here.
Thank you, and thank you for the introduction. So we've heard today a lot about how MPC works and what can be done and what are the barriers. I think I maybe, you know, in the last talk, I will not tell you about our machine optimizing machine learning algorithms in MPC, but rather I will tell you about why should anyone use MPC. So you saw this slide. Rivo was talking about what Cybernetica has been doing with MPC, and the development of ShareMind started in 2007. I started working with ShareMind in 2009, so you can calculate how many years that has been. And while we went live in 2011 with real data, and we did different kinds of already real data analysis on tens of millions of records in 2015, we really cannot talk about is it scalable or not. Simple statistics has been scalable for 10 years. Now, I think the problem is somewhere else. Scalability, yes, it is an issue, but I don't think it's the barrier that is going to be the kill technology kind of barrier. So I think I've tried to figure out what is the incentive to get people or organizations to use MPC. So I will now talk about a couple of the cases and discuss why these cases basically did decide to go for MPC. So the first one that Rivo also mentioned was the one where we did a study using Estonian government data from 2 different government data sets. One of them was the education database and the other was the financial database. What we did was we tried to find out why computer science students don't graduate on time. Whether this is because they work during their studies or whether this is for some other reason. Now, you're all wondering why. It is not because they work during their studies. It is for other reasons. Who knows what, but you know, it's not because of that. Especially if they work in IT fields, then they tend to graduate more on time than not. Anyway, so why this study actually ended up being done under MPC was because the organizations, the statistician or the center that did the study, they basically could get data without MPC as well for bachelor students. However, for master students, data from the Ministry of Finance or the financial data, that was so sensitive that they were only able to give it out in anonymized form. So, and in Estonia, we don't have a lot of people. So the anonymization, like it was K anonymity, the K was 3. So it's not like you're aiming for a super complex group. So, and they still were not able to get the data. So they could not get these groups for master students because there are not enough people in Estonia and there are even less master students. And the groups were just so unique that you could always go back and identify someone from the groups. So here, MPC provided a tool to help do this analysis without anyone being able to see the data. Now, if you looked at the previous page, it said 2015. So if you now recall, then 2015 is before GDPR. We actually got an opinion from our data protection board saying that this is a sufficient measure for giving enough privacy for this statistical study to be performed. However, when GDPR came around, then it is more difficult to give this kind of opinion because in terms of GDPR, secure multi-party computation is still pseudonymization. And it should be because it's not anonymization. So we're not trying to use MPC to get out of GDPR free or whatever. We are trying to rather see it as a kind of beyond state-of-the-art measure. Because right now, GDPR says sufficient measures should be taken. This is a sufficient measure. It is actually beyond the state of the art because GDPR also says that state of the art should be used. So this could be one reason. However, the reason that where we could use it on real data in 2015 is a bit more difficult to get across. Okay, so the second reason is the study that was done last year by Ludwig Maximilians University in Munich. And they conducted a real live data study on international hospital data between different hospitals to research rare diseases. And here, if we ask why did they use MPC here? Well, the reason is, even though the principal investigator there had all the ethics committee approvals and data protection impact assessments to do this on open data, he just wanted to do better. He wanted to use the technology to use a more advanced technique to actually give more privacy to the patients whose data they were using. So, this brings me to the Eurostat project that also Rivo talked about, the Joconde project. Eurostat is also doing this because, again, I'm assuming, they are doing this because this is just a way of doing things to go beyond state of the art, to start to actually use the technologies that are available and to make them more available to different organizations. With statistics bureaus, it's always a case of it could be the case that if we cannot do this, we can just kind of change the legal basis to get us to be able to do this. And this has been, I've heard this kind of talk in different places that, okay, yes, let's change the legal basis so that we have the right to do this. But maybe that is not the way to actually do things. Maybe we can do better. Maybe we can try to use technology that is available and that is already at quite a high technical readiness level. The Estonian government in 2023 procured a roadmap on how to take privacy-enhancing technologies into use in Estonia. This is Cybernetica was involved in creating this roadmap, and even though there are quite very ambitious deadlines, then the the procurements are now slowly coming to life. So even governments are trying to use the technologies to let's say, give more reassurance to the population on using their data. Because when we're using government data, then a lot of the times people, the data there is not so much consent-based, rather than it is, again, a legal basis-based data collection there. Okay, so now coming to why we should use MPC, and because secure multi-party computation supports privacy by design, which is a thing that our legislation is also asking, but it is something also that is inherently a thing that we strive for. It enables the creation of new services. Data that could not be used before can be usable with secure multi-party computation. It can become easier to use different data sets when you're using multi-party computation. And it also protects both personal and corporate data. What I mean here is that it's not only a privacy-preserving technology, but it also preserves confidentiality of data. So it's not just the personal data, but also financial corporate data. When we are using different pseudonymization methods, let's say other than MPC, or anonymization, we lose in accuracy. So using MPC instead could give us more accurate results in our studies. The regulation, what we need is support from the regulation, and I've heard this today before, that from questions as well, that it's really not, you just cannot understand, and you cannot, it's not easy to define MPC in terms of GDPR, or kind of use GDPR to define MPC. So this is a thing that we have to work towards to make this clear. We need some kind of legal precedent from somewhere where it works. But again, it's really difficult to do a step. And as Hossein also said, that it depends. And until there is some kind of legal precedent, it will always just depend. One of the issues to use MPC is to avoid the liability that might come from misuse of data. So you can do this during processing of data. Of course, you need other measures as well, because you will need out privacy. It is not going to be, if you do something under MPC, then afterwards, when you publish it, you still need to take care that you don't publish too much. We do have European values of privacy, and I think MPC supports these very well. So we should be striving for that. And of course, we all care about privacy. So let's use MPC.
Thank you very much, Liina. Well, we'll now open for a short Q&A among the panelists. I will be the one kicking the Q&A, but I'm waiting for any questions from your side. And I'm actually combining two questions that I had written down, which I would like to address to all the speakers. So we heard that Thomas Lorünser was mentioned that they're incentivizing this technology stuff. I would like to hear from you what in your personal organizational obstacles to embedding secure multi-party computation, and to actually bring it on a large-scale, real-time, feasible system. And I would connect that as well with what would be how can we balance the trade between the accuracy of cryptography and the efficiency, the computational efficiency in secure multi-party computation? Please.
All right, I have the microphone, so maybe I start. Yeah, so your first question about the obstacles, I mean, that's right in the ballpark that I was mentioning at the very beginning of my talk. I observe, and I think others here observed already, that deployment issues, selecting the nodes, talking to the node providers, legal issues local to the node providers, perhaps, sysadmin DevOps issues at the node provider side, or obstacles that cost time, energy, money, and so on and so forth. And having a more seamless way to do this. For example, if there would be an available network where we could have lots of different nodes that would all be used to running MPC use cases, where you as a use case provider would select the nodes, deploy your Kubernetes installation with a press of a button, and that would basically take care of all these issues, then at least that obstacle would be gone. So I think that's something that is not impossible to do, and I think that's on the horizon. You had a second question as well. I forgot. What was the?
Not sure. Yeah, my second question had actually to do with that. With if we could make a wish, let's say, and we could say these the technical or organizational developments that will allow this technology to outstretch to a larger dimension. Well, to identify which ones those would be.
Also accuracy and scalability.
Yes.
Remember again, yeah. Yeah, so I think there's no technological obstacles per se. I mean, I have this techno-optimist view here, I guess, but I think what is somewhat missing, but that's maybe an easy thing, is more investments. So I can imagine it's only a matter of time and money, basically, to get this off the ground. But I wonder what my fellow co-panelists have to say here.
For the barriers from the deployments, I would say that the kind of because your system now works with 3 different organizations that are non-colluding. Hence, they have different, also different administrative teams, and it's going to be more difficult to synchronize the computation between these if they are because they need to be in different centers, different hosting centers as well. If we're talking about cloud, then they have to be at different cloud providers. So the barrier there is that you're going to have to coordinate this. These parties, however many there are, to be working in a synchronized manner, but also if one of the nodes falls, then what is the availability there, and how to get it back up and then to connect to other nodes. So to have this kind of availability issue to be solved. In addition to everything else. I do agree with what you said. It's just this is also, I think, one of the barriers there. As for the, because one of the obstacles that's also there is when we are talking about cloud-based systems, because not if we're talking about huge data sets and a lot of data analysis and computing power, then we are going to be talking about clouds. And when we talk about clouds, then between the different cloud providers, it's going to be very expensive to move the data. So the communication is going to be very costly. So somehow to solve that issue, and I don't think it's just, throwing money at it. that too, investment helps, super. But this is going to be an upkeep cost for everything. It's going to be there for, if someone is going to run the system for years, it's going to be there for years. So there needs to be some kind of solution for that, to have, I don't know, some kind of dedicated system for this, and not having it be the usual prices of cloud-to-cloud communication.
Okay. Yeah, I think the different perspectives I'm seeing it is the convenience perspective. I think we need an easy way for people to use it for non-cryptographer and non-MPC companies. So I see it more like this should be an infrastructure which I can access. So we would need, I think we would need, I won't go that far that we need it like a railway system or something like that, but we need certified cloud providers which can act as a node, which also delete the data after computing. I mean, it doesn't stop if they keep the data and collude later. So there's so many pitfalls in implementing it. I think we need a reliable infrastructure for that, and we need standards to do that, to have interoperability, that one compute node from one provider could compute with the other one from the other provider. So this is something like an infrastructure would be nice, based on open standards and make it accessible for the people. And for sure, we need the legal side. I think we should clarify the role of pets in GDPR or in compliance systems, NIS, whatever. I think they should get a clear role there and that a benefit. Because what if I'm a small company or a big company? Why should I use MPC if I'm not an MPC company? But what's the benefit for it? So I can do everything on a contractual level if I want. I do some service level agreements and I'm fine. And I can get rid of all the mess and be compliant, except if I want to have a USP beyond state of the art. But I think we should really push the boundaries of state of the art. And I would wish that we have something like an MPC infrastructure, which is just there to use.
I have a very quick follow-up question to you, Thomas, because of what you mentioned. Do you think that for SMPC to thrive, we need to hide its complexity? It's absolutely, let's say, a needed thing to do, to hide that?
Yeah, but I have a payload I want to compute on this data, and who can help me? I could imagine if I'm an engineer but not a cryptographic engineer, but a system architect or whatever, then I have a task to compute and I want to distribute it. But then I have to rely that the nodes are certified, they don't collude, but I don't want to make 3 contracts with 3 cloud providers and setting up all IP addresses and maintaining that. But I want just say what I want to have computed, and hopefully there is an infrastructure and a regulation behind and certification behind. So like I do cloud computing now, but I don't want to trust the cloud provider anymore. So something like that.
Well, I totally agree with her that one of the main problems is the synchronization. And having like an infrastructure, as you say, it could be a good idea to address this synchronization and also to allow to non-experts to use secure multi-party computation. But the problems and what I have tried to explain in my presentation is what you say about the certificates, how you trust this infrastructure, and how do you know that they are going to really compute what you want to compute. And also, how do you know that they are not going to collude? So you have to have like a trust in that infrastructure. And that is one of the problems that we have to solve.
Right. So in terms of the obstacles, I think one of the obstacles that was not mentioned is maybe the gap between theory and practice that we see. So it's not that you like throw some code over the fence to like 3 different node providers and they just deploy it. It's also a lot about details, like you shouldn't have a single engineer who can just like run an update on all those nodes, right? Because then you haven't won anything. So you need some governance structure as well. And there are many of those kind of things that at least we have experienced when building those systems. And this paired with the fact that there are not so many experts out there, you need to find those experts, you need to hire those experts in order to get something off the ground is actually not that easy. So I think overall, like, this was at least the biggest obstacle for us, not necessarily the technical one, but like more the organizational one. And my hope is like that with the growing interest in data privacy, that more and more people will jump on that, that there will be more and more abstraction layers over time, and it will be just become more and more convenient and easy for everyone to build those systems.
Thank you. We have questions. Thanks. We have time for, I would say, 2 questions, and then we need to wrap up because we're already out of time. Thank you, Mike.
It's a really quick one. So thanks a lot for your inputs. Yeah, you can hear. Okay. The way that software is developed these days is currently largely impacted by using artificial intelligence. So when you develop source code, you always get some support from, let's say, Claude or ChatGPT. So my question to the panelists would be, imagine that Claude would see, hey, you're trying to do this. Maybe you should use MPC. I can configure it for you. I can roll that out for you. I can take care of all the configuration houses that you need experts for. I'm an AI, I can do that. Is that a bright future or a horror vision?
I teach a privacy course in the University of Tartu, and we had an exam this year. And basically, we had a task, and they had to answer. They had to basically say what technologies they would use, what privacy-enhancing technologies they would use. And well, it's a home exam, so everyone was using ChatGPT, and they asked, and I got this one woman sent me her ChatGPT log, and it was amazing. Like, she was basically, ChatGPT did not think that MPC was a thing at all at first. So she asked, what about trusted execution environments? And ChatGPT was, oh, that's a great idea, blah, blah, blah. And then she asked, what about MPC? And ChatGPT was like, no, that's going to be too expensive. It's going to be time consuming. It's going to be bad communication. So right now, somehow, at least ChatGPT, which is the thing that most people are using, has the idea from somewhere, I wonder where that has come from, that MPC is expensive, it takes a lot of communication, it is slow, and unfortunately right now, it is not going to suggest that you use MPC. It might change, but this could be a future, but right now, no. I'm not, yeah, it was trained, but I don't think it was purposefully trained. It was trained based on input information. Sorry, I grabbed the mic from you.
Okay, Jaap Koopman, Radboud University Nijmegen. Question for Christian too. Just triggered by your remark about like you need to protect against like insider jobs. In your system, you explained this secret sharing stuff. Is there any like cryptographic guarantee that you cannot reconstruct the template from the individual shares that's stored on the servers?
So you mean like whether you can go from the iris code back to an image, or? No,
because that you cannot probably do. But I don't know how that works. But from the shares back to the iris code.
I mean, of course, if all the 3 shares would collide, you could go back to the iris code. I mean, that's.
But isn't that dangerous? Given the fact that that iris code is basically giving access to, in the end, everything. I mean, that's your world vision, I guess.
I mean, that's true. It's a tough question. But at least we haven't found a way of like completely sorting that out. That was basically the best approach that we have found to make things more secure.
Okay.
I hope
maybe some work to do there, I guess.
I mean, we're constantly evolving the system. I think we already came a long way from like starting with raw iris codes to like SMPC shares. Of course, there are always things to improve. We're constantly working on that. If you have some ideas, I'm happy to hear them.
Let's see. Thanks.
So I'm very happy that private biometrics was mentioned in 3 of your talks. And the first academic paper was at PETS 2009, 16 years ago, where people started to think about private biometrics with Payet and super slow crypto back then. And I'm super happy to see that there's actual, we can do thousands of iris matches or millions within a second these days. And the thing is, if we in Europe don't care what Liina said in the very end, if we in Europe don't care about privacy, who else in the world would care about privacy, or who remains to care about privacy? And my question would be, what was also mentioned, how can we make MPC at least the state of the art or even beyond state of the art on a regular basis? Like this takes decades also to rewrite law and things progress very slow. But we don't know yet what will happen in 10 years. So we should really get going now and have MPC as the state of the art, at least for protecting privacy here in Europe. The rest of the world, I have little hopes, but at least we in Europe, and this also goes maybe to the organizers. Thanks for hosting this event. We in Europe should talk about these privacy enhancing technologies and bring them on the street and also into the legal regulations.
It was such a good question that we'll leave it in the air, I'm afraid. Thank you very, very much for that, Thomas.